Well, the decades-long hunt for the so-called God particle may soon be over. They believe the so-called Higgs Boson particle is key to explaining what gives mass to our bodies and to the world in general. Physicist Michio Kaku joins us now to explain, do they actually find the God particle, or are they just certain that it exists?
$10 billion have been spent to find the Higgs boson. The latest rumors are that they found something. They found a spike in the data, but they're not quite sure that it's the Higgs boson. Now remember that if it's not the Higgs boson, we physicists are going to have a heart attack. The foundations of modern physics will crumble if we don't find that darn particle.
And tell me why I care so much if we find this bang. I mean, how does it affect me? What's the key thing that I take away from this?
The origin of everything stems on this experiment.
It is the big question.
Okay, I don't want to make too many words, and I ask Joe Incandela from CMS to take the floor.
Okay. Pile up. We've eliminated the impact of pile up. Pile up, this is background and this is data. Least background, a little bit more background. Remove jets from pile up and cross checks. Look at all this data to try and extract a fairly significant signal. Main backgrounds, reducible backgrounds, nice symmetric distribution now. Reducible backgrounds from data, reducible backgrounds data, discrimination between background and signal. Signal, background. Here's the data. Comparing to background, signal for all the backgrounds is rather well distributed. Reducible backgrounds, background is really signal. If we combine the ZZ and gamma gamma, a combined significance of 5 standard deviations.
Now we go immediately to Atlas Fabiola Gianotti, please.
Thank you. It's not easy to speak second because all the clever things have been already said. Anyway, so pile up. Backgrounds, pile up. Pile up is the challenge in 2012. As you can see, pile up, which is pile up is to pile up of pile up. The signal to background ratio, pile up with pile up is pile up. Irreducible background to pile up. Reducible backgrounds, pile up of a huge background. As a function of pile up, to extract an error peak on top of this huge background signal from pile up background. This means mission accomplished in the rejection of this background. Pile up, subtraction of the background, background, which can pile up. Let's move to the result. Reducible background, the signal, the reducible background, and here we have an excess of one big spike here, in this region here. This is 0 cents.
As a layman, I would now say,
we have banged the Higgs boson.
Why it banged? How it banged? The Higgs boson could explain the spark that set off the Big Bang.
She banged the Higgs boson.
It's wonderful to be at a physics event where there is applause like there is at a football game. Congratulations to everyone.
we have a discovery. We have observed a new particle consistent with a Higgs boson. Which one? That remains open.
Which one? Wow! Now that physics has reached climax and the LHC is in afterglow, so to speak, how do we make sense of it all?
I've been to the BBC canteen. Now I want you to imagine that it's the Big Bang. Way back then, we didn't have a Higgs mechanism, okay? So they're going around through the universe at light speed. Now, unless some of these particles have mass, they can't clump together. Everything in the universe that we know would not happen unless they have mass. Now, a few fractions of a second after the Higgs mechanism, after the Big Bang, we get the Higgs mechanism permeating the whole of space. So now we have the Higgs mechanism permeating the whole of space. That interacts with our particles. Now some particles, as they move through the Higgs mechanism, get very bogged down. and they become very, very massive. And there's one sort of particle, this one's called a photon, has no mass whatsoever, and that continues to fly off at light speed. Okay? But that essentially is what the Higgs mechanism is, and that is one of the particles in the Higgs field itself. That's what they think they've done today, and that helps them explain just why everything has substance, why it has mass.
In a BBC documentary about the search for the Higgs boson, which aired prior to the July 4th announcement,
just before Christmas, researchers working at CERN near Geneva announced that they'd caught a tantalizing glimpse of the Higgs boson. It'll be evidence for one of the most all-encompassing ideas in physics, that at the heart of everything is the simple and enchanting idea of symmetry. As the heat and fury ebbed out of the Big Bang, so the theory goes, the Higgs field condensed. As particles travel through this field, they get slowed down, like traveling through treacle. This is what gives them mass. After decades of work, the LEP collider at CERN, a predecessor of the LHC, ruled out the Higgs being at the bottom end of potential masses. And by November 2011, the LHC had already radically narrowed the search. The new lower limit has risen to 115 GeV, and the new upper limit has dropped to 127 GeV.
The reason the LHC experiments weren't able to exclude anything inside this remaining window is that in fact they see an excess of events.
And the excesses were in practically the same place. CMS observed one at 124 GeV and Atlas one at 126.
there was a little insignificant variance mentioned. It appeared that CMS and Atlas were detecting different particles.
This slight gap between the CMS and Atlas data has never been elaborated on or addressed again to my knowledge. While I was combing over the data of CMS and Atlas, their July 4th, 2012 results regarding their search for the Higgs boson, I noticed again this same pattern, but this time it was inescapable.
These are the two high sensitivity channels.
The channels he is referring to are the ZZ and gamma-gamma signals, the two channels that had an excess of events significantly greater than that of the background.
This is adding the W. Now if we add the other two channels, we fall below 5 sigma.
When added to the statistical analysis of the data, they lower the p-value of the data by 1 sigma.
And we appear to be, we would have expected 5.9, so we appear to be about a sigma below where our expectations are.
These missing signals of the Higgs boson adversely affect the data, indicating that a new Higgs particle theory, one absent these two channels, is needed.
Which is not dramatic yet. We'll have to see how things go with more data.
In other words, these are the only two signals of the Higgs boson that match prediction by the standard model.
What we looked at too was how well the W and ZZ channels are performing relative to each other, because you expect custodial symmetry, so it's consistent.
Even cross-checks of the experiment indicate that systematic error cannot be blamed for the missing signals.
So to quantify the excess, the usual p-value plot, already shown before, which quantify the consistency of the data with the background only expectation. So if you are below 1 sigma, you are fully consistent with the background at the 1 sigma level. If you are beyond that, you have a different level of consistency.
So if sigma is 1 or higher, then we have something to talk about. If sigma is less than 1, we have nothing more than background.
So you can see that the largest deviation is observed for a Higgs mass of 126 GeV. It is at the level of 3 sigma, and this is how the excess shares among the various channels. It is driven by X2 gamma gamma and X2 4 leptons.
Let me repeat. These p-values correspond with the ZZ and gamma-gamma signals. Notice that the BB and tau-tau channels are missing. Why?
While X2 WW doesn't bring much. So although this observation is in good agreement with that expected from the standard model, it's also very well compatible with the background. So it's not really conclusive.
Since the missing signal from the other channels is more consistent with the background than the standard model, the data is not conclusive regarding the standard model version of the Higgs boson.
Here we observe 190 events and we expect 147, so you see the observation, we have an excess. The observation is 30% larger than what we expect, in agreement with our measurement of the ZZ cross-section.
She is discussing that there is an excess in the Z channel, specifically greater than that predicted by the standard model.
In general, we have observed some excess in the data in dye boson compared to the prediction, so there is some work still to be done with our friends theorists. But anyway, the impact of this excess on the low mass region has been checked carefully, and it's totally negligible.
Even though this excess is clouding the data, so to speak, it isn't enough to cover for the missing channels.
An expected significance from a standard model Higgs boson of 4.6 sigma. So you can already see here the compatibility between what you observe and what we expect from a standard model Higgs boson.
Thus a need for a theoretical adjustment.
What is the consistency between these results? We observe an excess in X24 lepton and gamma-gamma. You may remember that the maximum of the excess was at 125 GeV for 4 leptons, at 126.5 GeV for gamma-gamma. What is the consistency? So we have made a two-dimensional likelihood fit to the mass and the signal strength for X2 gamma-gamma and X24 leptons, and these are the results. You can see here the curves, and I don't have to spend much time to convince you that there is compatibility at this level of fluctuation and statistics.
Something hit me when I saw this chart, because it was the third piece of a puzzle that matched two other pieces that didn't make sense until now. Are we dealing with one type of Higgs particle, or more? Going back to the BBC documentary, the CMS and ATLAS data, and my notes from 2004, what I found was a major discovery. Not only did I see something significant in the data that seemed to have missed everyone, it just so happened to confirm exactly what I was predicting back in 2004. In order to illustrate this, let's first examine the LHC, and then let's go make our own, shall we?
CERN's spectacular Large Hadron Collider. Hydrogen atoms from this gas cylinder are fed at a precisely controlled rate into the source chamber of a linear accelerator, where their electrons are stripped off to leave hydrogen nuclei. These are protons and have a positive charge, enabling them to be accelerated by an electric field. Their journey to eventually take part in ultra-high energy collisions. By the time this packet of protons leaves Linac 2, it'll be travelling at 1/3 the speed of light. The packet is divided up into 4. In order to accelerate the packets, they are repeatedly circulated, and the electric field is now pulsed. Powerful electromagnets are used to bend the beam of protons round the circle. The booster accelerates the protons up to 91.6% of the speed of light. Recombining the packet from the 4 rings, it's then flung on into the proton synchrotron. Let's just follow 2 such proton packets, reaching over 99.9% of the velocity of light.
Taking a closer look at this animation illustrating the formation of the proton beams, it becomes apparent that there are several ways the protons could be entangled, given their proximity and relativistic speeds. Quantum entanglement occurs when particles interact physically and are then separated such that pairs of particles are properly described as having the same quantum numbers or states. When a measurement is made on one of the particles, it causes the particles to take on a definite value. The other entangled particle will be found to have taken on the appropriately correlated value. This correlation is observed even if the entangled pair has been separated over long distances.
The added energy manifests itself as increasing mass of the protons. In short, the protons can't go faster, so they get heavier. The packets of protons are now channeled into stage 4, the superproton synchrotron. Soon, the packets of protons will be energized sufficiently to be launched into the orbit of the gigantic Large Hadron Collider, or LHC. There are 2 vacuum pipes within the LHC containing proton beams travelling in opposite directions. Using ultra-sophisticated kickers to synchronize incoming packets with those already circulating, one vacuum pipe has injected into it protons which will circulate clockwise, and the other protons which will circulate anti-clockwise.
Applying concepts found in the classic double-slit experiment, the LHC can be viewed as a double slit. The entanglement between events at CMS and ATLAS reflect interference pattern within the experimental results.
The counter-rotating beams cross over in the 4 detector caverns, where they can be made to collide, and it's the debris from these collisions that is tracked in the detectors. For half an hour, the SPS injects protons. Finally, there are 2,808 packets. Each proton, whose velocity is now so near the speed of light that it goes round the 27-kilometre ring over 11,000 times each second. Now the protons are ready to collide in the detectors. A steering magnet finally brings them onto a collision course.
What do I mean by a double slit experiment? Well, first, let's familiarize ourselves with a double slit experiment. In this Discovery Channel documentary, the bizarre nature of quantum behavior is illustrated through an actual double slit experiment.
This simple configuration shoots particles of light called photons, one at a time, through 2 tiny slits in a screen. Since the photons travel one by one, some through this slit, some through that slit, you would expect them to leave a pattern of 2 stripes on the wall. And you would be wrong. They mysteriously create a band of stripes. This is what you would expect to see if a constant beam of light shined through the 2 slits. It would spread across the wall like a wave. So how can single bullet-like particles of light create a wave pattern? This could only happen if the particles go through both slits at the same time. In other words, the particle is in 2 places at once. But strangest of all is what happens when you put detectors next to the slits. When the photons are being watched, the wave pattern disappears. Take away the detectors, and the wave pattern comes back.
Looking at the construction of the LHC and seeing that where the proton beam splitter is in relation to the beam cleaning mechanisms, that because one of the distances that the proton beam travels after it's been split is shorter than the other distance, that the beam cleaning mechanisms cannot eliminate entanglement, even though they are, for the most part, eliminating most of the excess halo. So if you think about the delayed choice experiment, you can see how this would apply, and that we can still get entanglement between the events in CMS and ATLAS if we're presuming there to be 2 versions of the Higgs particles that are entangled for some reason that the LHC experiment is capturing. Rather than being averaged together, what if there were 2 Higgs particles being detected? One with a lighter mass, say 124 GeV, and the other with a larger mass, say 126 GeV. I've arranged the p-values, the channels, and the mass information in such a way that we can see the bizarre behavior the Higgs particle is displaying at the LHC. If we look at the channel information, it becomes real apparent that we have a mass to channel relationship that reverses at CMS and ATLAS. The Higgs to gamma-gamma channel is associated with the lighter mass with the CMS data, yet the Higgs to gamma-gamma channel in the ATLAS data is associated with the larger particle, and then likewise the Higgs to ZZ channel is associated with the heavier particle with CMS, and the Higgs to ZZ channel is associated with the lighter particle with ATLAS. And at the same time, the mass distribution between the heavier and the lighter particle is maintaining a more or less similar p-value between CMS and ATLAS, such that we can argue very easily that CMS is detecting lighter masses on average than ATLAS, and ATLAS is detecting heavier masses on average than CMS. Herein lies a problem. If we assume that there is only one type of Higgs particle reflected in the data, then there is an asymmetry in the mass distribution leaning towards the 126 GeV, and the decay mode p-values are inversely correlated between the CMS and ATLAS results, mysteriously, which is more indicative of two types of Higgs particles being reflected in the data. Furthermore, if there were only one type of Higgs particle being detected, in order to maintain the slanted mass distribution consistent between CMS and ATLAS, while at the same time maintaining the inversely correlated decay mode channels we see in both CMS and ATLAS data sets together, the Higgs particle events would need to be entangled between detectors. Half of a Higgs particle event would need to occur first in one of the detectors, while the other half of the same Higgs particle event would occur subsequently in the other detector. For instance, if one half of the Higgs particle event occurs at CMS, then the other correlated one half of the same event would subsequently occur in ATLAS, and/or vice versa. In other words, a single Higgs particle event would have to be spread across two different detectors sequentially. But this cannot be the case, because the decay mode channels are from different Higgs events at the different detectors separately. To illustrate this paradox even more, if we assume that we have two Higgs particles, the H plus and the H minus, the question becomes, okay, well, which one happens at ATLAS? Which one happens at CMS? If we follow one of the possibilities where it happened, let's say at ATLAS, because it did not happen at CMS, well, then the question is, why do we have the channels for the H plus spread across ATLAS and CMS, and the same for H minus? In other words, we have the channels for one or the other particle spread across both detectors. But if we assume that there's just one particle and we run through the data the same way, what we end up with is sort of a similar problem, and that is that we have the same Higgs event being spread across more than one detection in order to maintain and account for the mass distribution between ATLAS and CMS, and also the reversing of the mass channel relationship, if you will. There could be two different types of Higgs particles, one with a mass towards 126 GeV, H+, and another with a mass towards 124 GeV, H-, and that, for some reason, the H+ type is detected more at ATLAS and the H- type is detected more at CMS. Design variations between detectors could arguably account for this. Down here, if you'll look, we're going to go ahead and associate H0 with the idealized standard model Higgs of 125 GeV, and then we're going to go ahead and associate H+ with the heavier version of the Higgs, and H- with the lighter version of the Higgs. There are already Higgs models that incorporate an H+ and an H- And there is some similarity between those theory of the Higgs and what we're about to do. However, this is not the same thing, so don't get these two confused. In order to illustrate this double slit experiment, we're going to need our own LHC. Let's go ahead and just make our own. However, I don't have $10 billion, do you? So, this'll have to do, but I think it will serve our purposes just fine. Assuming that there are two different types of entangled Higgs particles occurring in either CMS or Atlas congruently, if one type of Higgs particle is detected in one detector, then, through an action at a distance, due to entanglement, the other type of Higgs particle would be detected in the other detector, or vice versa. In this way, to get the slanted mass distribution consistent between detectors while at the same time maintaining inversely correlated decay mode channels, if one half of the Higgs particle events of one type occur in CMS, then the other half of the Higgs particle events of the other type of Higgs particle should occur in Atlas, and vice versa. However, comparing CMS and Atlas data, it appears that half of the decay mode channels of one type of Higgs particle events happen in one detector, while the other half happen in the other detector. One half of the Higgs plus decay mode channels and one half of the H minus Higgs decay mode channels occur in one of the detectors, and the apparent correlated decay mode channel occurs in the other detector. But this cannot be the case either, because as stated before, we cannot have a single Higgs particle event spread across two detectors. Only one type of Higgs particle event can occur in one or the other detectors at a time, not both. A single event cannot be spread between detectors. One Higgs particle event in each detector at a time. In other words,
if it is assumed that there is one type of Higgs particle, it appears as though it is one particle in two places at the same time, suggesting two types of Higgs particle. However, if it is assumed that there are two types of Higgs particles in some kind of entanglement, then the particles appear to be in the same place at the same time, suggesting one type of Higgs particle.
what are we dealing with here? The concept of identity crisis and how it relates to quantum entanglement is captured very well with this ongoing Higgs particle search that's going on at the LHC. The idea of the inclusion principle in relation to the exclusion principle can be used to not only describe what I call identity crisis, but even more interesting, a new concept called cross-conjugation. And what I believe is going on at the LHC is that the data between Atlas and CMS is representing quite well this concept of cross-conjugation, or what I also call cross-symmetry. Well, as it would turn out, this was another phenomena I've been looking for to verify a radical new concept for physics, namely identity crisis. Here we have what I call the Bose condensed Higgs, which more or less is the same thing as the standard model Higgs with the idealized 125 GeV. And in the existence equations, given that the Bose condensed Higgs is its own self-conjugate pair, for lack of better terminology, we'll go ahead and have it as the same particle relative to itself, so 125 GeV over 125 GeV, giving us 1. So the identity constant being 1 reflects that the Bose condensed Higgs is one and the same of itself. Whereas the inflated Higgs, we have a Higgs plus and a Higgs minus. One is associated more with displacement energy, one is more associated with rest mass. One is associated with being in the future or moving forward in time. One is associated as being in the past or moving in reverse time. This particular Higgs field, if you will, is in 3 dimensions of time. It's the Bose-condensed Higgs inflated or expanded into a 3-dimensional time space where there's 3 dimensions of time and 3 dimensions of space. And here we go ahead and use the basic existence equations to derive the 126 and the 124 GeV respectively as an approximation to show that the existence equations work quite well in accounting for the Higgs mechanism. What we have here is the Higgs particle data in relation to spatial coordinates, and here we have the Higgs data in relation to temporal coordinates. If you recall, in the existence equations, the Higgs particle relative to itself, which we're going to associate with the standard model Higgs, the Higgs plus with 126 GeV, we're going to assume has more momentum than the Higgs with 124. So in relation to position, the heavier Higgs particle is further along. However, because the heavier Higgs particle has more momentum, time relative to it is slower than time relative to the Higgs particle with less momentum, so it's further into the past, whereas the lighter particle is further into the future. So this frame of reference corresponds with temporal coordinates. When we take the spatial coordinates and the temporal coordinates and apply them together through cross-symmetry or cross-conjugation, what we're able to do is superimpose these 2 reference frames on top of one another, and what we can see is we end up with an identity crisis. Do we have 2 particles, an H plus and an H minus? If so, where is one or the other? And if not 2, do we have 1 particle? Do we have the conventional standard model Higgs, or do we have the H plus and the H minus as reflected in the CMS and ATLAS data? Or do we have an identity crisis, which is basically both at the same time? In layman terms, an identity crisis is when 2 particles' quantum states are in close enough proximity with each other that they become both 1 particle in 2 places and at the same time 2 particles in the same place at the same time. In other words, their identities are indistinguishable and there is interference in the wave function of both particles. It is verification of a newly discovered aspect of quantum entanglement, the inclusion principle. Together, through quantum entanglement, the exclusion principle and now inclusion principle can be used to account for not 1, not 2, not 3, but all 4 known forces, not only preserving and completing the standard model, but tying it all to gravity in the most shocking way imaginable. And it is all startlingly consistent with experiment. The existence equations, as a simple approximation, can be used to unpack what may be experimental confirmation of identity crisis, other new physics principles, and their association with the Higgs boson. Further results from the LHC, CMS, and ATLAS should shed more light on this recently discovered mystery, the Higgs Paradox.